So now we know all about images formed by reflection, but there are a great many more applications of images formed by refraction, which is what we'll study now. Light converging into an image at a focal point by means of refraction is how lenses work, and so by studying this, we can make sense of refractive optical systems like your glasses. And many complex optical systems make use of both reflection and refraction with multiple lenses, multiple curved surfaces, multiple flat mirrors to achieve the type of image that's desired. It's a little stormy out, so if you hear thunder, that's what it is. To achieve the image that's desired from the typical object that is pointed at. So telescopes, binoculars, cameras, they're all examples of this. But we're going to build up from the basics, just like we did before. So our goal, same as before, is to find the relationship between the object distance, the image distance, and the radius of curvature. And we'll take an identical approach as we did for the spherical mirror, except now, instead of the law of reflection, we have Snell's law, or the law of refraction. So here's our picture that we're going to be working with. So we're going to have a spherical material, drawn nice and big, and we have an optical axis that's somewhere in here like this. This is going to be our vertex right here. Here is our center of curvature, like that. And we're going to have an object point back here, column P. And we're going to consider a couple useful rays, just like usual. So we're going to have the ray that goes directly in, right? And this is refraction, and so it's going to transmit right through the material there instead of reflect off the surface. So already we're different from before. So it's emanating out from the object. And actually, I don't know why I stopped at the center of curvature. We'll just keep going. And who knows what happens at the very, very end there if he refracts and transmits through, but we'll just draw it that far. And then we're going to consider another ray that goes towards the top of this system. So maybe something like this. All right, so it's emanating out like that. And at this point, we can consider, just like before with the spherical mirror, but now we have refraction as spherical surface, we can consider that this is the normal to the surface at that point. And we can call this point B. I guess I'll do it in here. B, that point right there where it hits. And we can label this height from point B down to our optical axis. We're going to label that H, just like before, which makes, put V up there so that we can put our delta right there. And we can also, while I'm at it, we can label the center of curvature R, and we'll just do it right to this point B because it'll be useful for the triangles that we're going to consider, just like before. So that is our radius, R. And let's pick back up with this ray. So it refracts at this point. And I'll tell you it'll refract something like this, right? I don't know, maybe it'll be somewhere in here, right? It's certainly not going to do this. It's not a mirror, so it's not going to do that. But I'll tell you it's going to be somewhere around here. And we're going to go through our derivation to find out just exactly where P prime lies. Oops. And, we're not getting coordinates for P prime. But because we are finding the object and image distance, image distance being this, we kind of do have coordinates for p prime. So that may have been obscured last time because I didn't say that very clearly. But we kind of are finding where it is and verifying the position because we know these distances here, right? This is s for our object distance, and this is s prime for our image distance. And so we know that it'll lie on the optical axis, and since we know that that length there, we know exactly where p prime is. All right, so number of things that we have to consider, but one of them that I don't want to lack emphasis on is that this is refraction. And so we have a material here, right? This is some material. And out here is going to be some other material. And what that means in terms of refraction is they're going to have two different indices of refraction, right? So this is going to be, we'll call it NB, and out here is going to be NA. And we're going to consider the case that NA is less than NB. So out here is NA, and in here is some other material that has a larger index of refraction. And that's why it bends something like that, right? You can forget about the whole complexity of the spherical surface and just pretend that the surface was flat at that point with an angle of incidence like this, and so then an angle of refraction like that, and you can apply Snell's law to verify that it would look at least something close to that drawing. So that's where we're at here. So now let's pick out some angles that are useful to us. So here's our angle alpha, just like we did before. And we have a few triangles that are going to be made with that h. And so one of them is with that alpha, and then another one is with this phi, that right triangle that you can see developed with that one. And then the last one is this beta here. Very similar approach. We just have the law of refraction instead of the law of reflection. And then another angle that we're going to consider here is exactly what I just identified, is this angle of incidence. We're going to call it theta A, and the angle of refraction, which is what we're going to call it theta B, right? Because it refracts at that interface according to those angles relative to the normal. All right, and the last thing I'll add to this picture is we're going to have to consider some sign rules, right, to see what's positive, what's negative. So I'm just going to write this in here explicitly. This is incoming because it is yet to hit the refracting surface. And this is incoming. And then this is outgoing because it's going away from the refracting surface. And this is also outgoing. So those will help us to determine the signs of some of these quantities according to our three sign rules, which apply equally to reflection as they do refraction. So let's go through them. So the first one, and you can reference back when we talked about this, if you wrote them down, the first one has to do with object distance, right? So the object is on the same side as the incoming rays in this picture, so the object distance is positive. So you have positive object distance. The image distance is the second sign rule. Image is on the same side as the outgoing rays, so the image distance is also positive. And this is the first time I believe we've seen an example of this case. I may have mentioned it vaguely, but here it is. The outgoing ray is on the same side as the image because we have the image formed on the right of the refracting axis, or the refracting surface. And finally, radius of curvature. It's a convex surface. So the center of curvature is on the same side as the outgoing rays, so the radius is positive as well. So it's a convex surface, which with reflection meant that it was going to be negative, but it's relative to where the image is formed. So similar to the second sine rule with the image distance. So since the radius is on the same side as where the image is formed, then the radius is positive as well. So I'm going to just put a little plus sign there. All right, so they're all positive. So since the approach is identical to the reflection case, I'm not going to go quite as slowly as we went through it. But I don't think that you'll be left behind at all, because it's literally the same steps. The only difference is we're going to apply the law of refraction instead of law of reflection. So let me identify these triangles here. I think I went with green last time. So we have triangles PBC, which is here and then here. So there's a triangle. And we have triangle P prime BC. So it's from the image to the center of curvature. Whoops, got a little off there. So we have this triangle, right? This whole triangle and this whole triangle, basically. So looking at those two triangles, we can say something about our angles. So we have theta A is equal to, because of this same exterior angle theorem, right? Theta A is equal to alpha plus phi. And we can say that phi is equal to theta B plus beta, exterior angle theorem. All right, and then taking the tangents of alpha, beta, and phi, right? So now we're looking at different triangles. So we're looking at these right triangles here, doom, 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 and finally this big one, right? So this guy, and this guy. Get rid of all that junk. We can take the tangents of alpha, try to keep it in view. That would be equal to h over s plus that delta amount. Tangent of beta is equal to h over s prime minus that delta bit. And then tangent of phi is equal to h over r minus that delta amount. We're going to do the exact same thing, small angle approximation, right? So tangent of alpha is going to be about equal to alpha itself, because if alpha is much, much less than 1 radian, small angle approximation, right? And so therefore alpha, let me do better, alpha is equal to h over s plus that delta amount. But if you remember, what followed immediately was this is much, much smaller if we're taking tiny, tiny angles. So a good way to visualize it is, instead of this exaggerated picture that I've drawn, really we're considering angles that are like this, right? Much, much smaller than 1 radian. So if we consider that this is essentially 0, if we're taking a small angle approximation, oops, I should underline this one, then we can skip right to that guy and say that alpha is equal to h over s. And beta is equal to h over s prime, and phi is equal to h over r. All right, so this isn't cheating, it's not mathematical trickery, it just limits our solution, right? So we're not saying that this is a solution, we've solved all of the universe and everything, we're just saying we've solved this little thing given the conditions that we've assumed. To solve it for a more general scenario would involve something more involved, less trivial, and so we're not here to do that. So we're just making these assumptions, keeping in mind that our answer is going to be limited to what it is, and being satisfied for that for now. All right, and then here's the new part. So instead of the law of reflection, we now have the law of refraction to relate these angles, and so it's going to involve these index of refractions and these angles here, right? So we have the law of refraction being NA sine angle of incidence, which we labeled theta A, and B, sine angle of refraction. That's our law of refraction. All right. So, small angle approximation again. So let's think this one through. So we're not just throwing small angle, and it just feels meaningless. So remember I said you can think of, we're approaching like this, really. I've drawn an exaggerated picture, but we're approaching like that, right? So if a direct on the optical axis ray goes straight through, you can imagine that as you go up, it doesn't curve very much, right? Doesn't curve very much, but it begins to curve more and more the higher up you go, right? And so what we're considering in all of the, oops, let me draw that a little better. What we're considering in each of these is according to the normal. And do you see how the this angle here gets smaller and smaller and smaller, and also this angle here, right? Gets smaller and smaller the closer you get to hitting direct on. So it is actually valid to make a small angle approximation here. Yet again, it's consistent with us making that small angle assumption, so we have to keep that in mind. But since we're making it up there, that means that we're only considering those rays that are not quite as exaggerated as this guy, but really just like a tiny bit difference from that guy. And so we're making that small angle approximation, so that means that it applies here as well with these incident and refraction angles. So that means that if theta A and theta B are much, much less than 1 radian, then that means that sine theta A is about equal to theta A itself. Okay, so that means, oops, this is our little small angle approximation. So that means that we can just simply write NA theta A is equal to NB theta B. All right, so now we have all our equations. We got this guy, we got this guy, these three, and we have this one. Between all of those, we can put them together and find a useful equation that we're looking for. So here's how we're going to do it. So we're going to solve the previous equation that we just came up with for theta A. So theta A is equal to NB theta B over NA. And we're going to plug that into the very first equation that we wrote down. This guy there. So that means we get NB theta B over NA is equal to alpha plus phi. You follow so far? All right, and so now we're going to solve that for theta B. So we're just going to write theta B is equal to NA over NB times this alpha plus phi portion. Now we're going to substitute this into the second equation that we wrote down. So this guy, all the way up here into there. All right, so we got this guy on the left side, NA over NB is equal to, oops, with that alpha plus phi amount, is equal to theta B. Whoops, plugged it into the wrong side there. So this theta B gets plugged in there. And let me start over. There we go. All right, so we have phi being equal to NA over NB alpha plus phi. Okay, that's what we plugged in, plus beta. Alrighty. Which means that we have, if you were to write, expand this out, NB phi equals NA alpha plus NA alpha plus NB beta. Did I write that right? Yeah, that's right. Okay. So then we can group some things on the left and the right. So we have NB minus NA phi on the left, and NA alpha plus NB beta on the right. Alrighty, you follow that so far? If you don't, just pause. It'll take a couple seconds just to verify that algebra there if you didn't follow along in real time. So take our small angle approximated tangent expressions for alpha, beta, and phi, and we're going to plug them into the equation that we just arrived at. So now we're taking this guy, and that guy, and plugging them in, right? So we have NB minus NA, NA phi, which is h over r, is equal to NA h over s plus NB beta is equal to h over s prime. All right. And if you divide by that common factor h, eliminate that. And what you end up with, if I clean it up a little bit, and put things on the side that we're familiar with, them being NA over S plus NB over S prime is equal to NB minus NA over R. This is our final equation. So this is for the object image radius of curvature relationship for a spherical refracting surface, or interface maybe, but same difference. So just to evaluate what we arrived at, just like before, this equation does not contain the angle alpha. And so the image distance is the same for all paraxial rays emanating from point P, right? So in that final equation, it's not saying, oh, for specifically this given angle alpha. No, it's for any angle. This is the relationship between S, S prime, our indices of refraction, and our radius of curvature. And so for all paraxial rays, right, all of them that obey that small angle approximation, we have found the solution. We found the position P prime, right? Given these sign rules. So given that the object is outside of the thing, and that that it's a convex surface that it's hitting, yada yada yada. All right. So that is it. Hopefully that wasn't as painful as the first time we went through that process.